How's it going, everyone? Euler Gonzalez here again, and today we're going to take a look now at the advanced Redux. Specifically, what is the problem that this particular function called reducers works, and what is the problem that it solves? This is part of a series of videos of how to become a UI specialist, and especially in today's world that from Yifni Ray, a software engineer that previously worked at JetBrains over 3 years, and now he's currently at Meta. He made that particular course, which is something that we're taking notes out of that. As a way to understand is the core fundamentals of system design that allows to build scalable web applications, right? So that's one. And also, all right, is or as part of that, well, how can we now is as we know, the core fundamental of building is this or UI applications, as well as the JavaScript. How can we use JavaScript to build this UI rich interaction applications by using the object-oriented programming? What is this pattern, and what is the particular pattern that JavaScript actually is using, the prototype, as well as how can we now handle is this communication or this real-time communications that allow to these modern web applications to work in the way that we need. So for example, we need to start is how can we use is the callbacks, or how can we start to use is now some of the queue as a way to perform some async operations. So we start with the callback queue and then the promise, and then understand that behind the scene is using, depending of the environment that you are running your JavaScript application, whether it's Node or the front end, which is the browser, it use now a particularly callback queue, a way to process all of these async operations. So in the case of the browser, it use the callback queue, and when you want to process now this promise, which is the eventual completion of an asynchronous task to be completed in the future, which is now a object that represents this. Anytime you want to use a promise or any API, any promise-based API, it behind the scenes now use the micro tasking, right? Which has we have a more priority than the callback queue. And when you combine this tool to build these modern web applications that allow to communicate to other servers, right? With a combination of callback queue, promise, web API, the event loop, as well as the callback queue, the micro task, how all of these different components allow us to build these modern applications in JavaScript. This is covering the async nature, as well as understanding some of the particular patterns that the language allows to do. For example, closures, and now what closures enable us to do. So for example, the model pattern, as well as the immediately invoke function expressions, the iterator patterns. So we can create our own iterator, or this is a particular design pattern that anytime we encounter a typical problem, we come up with some solution, with the same solution to solve these common problems. And this is the iterators. And iterators is just part of the design pattern that allow us to, in the context of traverse data in a particular data structure, we don't care about which implementation that we need to do. We just only want to traverse the data structure. So So that's what we have is the iterator. We can create this iterator design patterns. And also, how now the iterator is just the entry point, the gateway to the generator. So the generator is now this combination of the iterator patterns and the ability to now, anytime you want to run a particular functionality, so you call that function, you run that functionality, and then you get out the function execution context. And when you need to call that function again, you do that again, right? So that's quite interesting, by the way. And with that, right? We also look that by mentioning, describing all of this, and especially in today's world that our companies now are using is some of these top tech tools that companies like Facebook or Google have created, right, to solve their specific problems. Now, in our case, we're gonna use React for that, and how now React actually allows us to describe the UI, okay, in a particular way that allows to provide interactivity. And then once we do that, we define inside of those components or all of these UI states, where now this particular states actually is the way of how you can now update the UI based on an input, based on a user interactions. And because of that, we need to find a way to manage that state. Okay, so how important is to think our UI state as state change, and also provide some structure or a state structure, as well as how can we now understand is the nature of React, especially when we need to reset or preserve the state, how React actually does that behind the scenes, so we eventually can share that state across different components, something known as lift a state up. And when it comes to make our life much more easy to maintain the states, especially when we need to update the state, especially the more inputs that we need to update, or the more input a particular state needs to react, the more it makes sense to use a reducer. So how this reducer function works, what is the value proposition of this reducer, and how now then we can actually share states across distinct components in a way that make our life much more easy. So instead of doing the props drill, we just use a context. And what are the trade-offs when you're using a context? Which is, because any times React automatically will trigger updates to all the child components that use that particular context, starting from the provider. There's some challenge and trade-off that you can do, especially as you do that. So all of this huge overview that I mentioned before, is just as a way to understand how do we get here. Why this is important? Because once you understand that, you will embrace complexity. And in this case, Redux is just this library, this well-battled test state management applications that allow us to solve some of these particular problems that we have as we build is React applications. So for example, we got now is the problem is how can we now manage our states, especially as I mentioned before, the more inputs we have to react, okay, or the more input a particular state needs to react, the more it makes sense to use a reducer. This function that it takes an initial state and yeah, this function that takes an initial state and interesting. This function that takes an initial state and an action to generate a new bit of action, to generate a new bit of state. So on that topic, right? The whole point of that is to, now that we are looking at here of Redux and why, what is the value proposition of this advanced Redux, right? Or AKA is Redux Toolkit, right? So, okay, Redux Toolkit, Redux Toolkit, known as RTK, okay? So what is the problem that this particular things solve? So, well, Redux after all, because it allows us to, well, make our life much more easy when it comes to manage states, app level states, users. For example, if you have an e-commerce, users, orders, history, that kind of data, also analytics. So anytime you need to do that, you need to create some sort of particularly files, or it's a particularly file path that you need to create as a way to make your state updates maintainable, easy to test and debug. Following is the Flux architecture pattern. We're not going to dive deep into much into that, but just understand that this Flux architecture is a way of how can we now create is a client-side applications, right? We also have is the MVC, which is the model view controller or model view controller. Okay, again, this is particularly way of how you can create is your front-end architecture. So MVC is actually something that a lot of applications that using is PHP or Python actually use that as a way to now is on the server, they're gonna get the data from the database based on a particularly query, right? Let's say the user is navigating to the product list, okay? As you navigate to the product list, now it is time for them to say, all right, let's make this query that the user wants to navigate, fetch the data from the database, the models, all right? And then in a controller, we're going to now construct is the data and the template that we're gonna send to the clients, populate that data in the template dynamically at runtime, and then serve that to the client. And this process is something that's known as the round trip. So because now people in the user and the market itself has pushing the boundaries as the way they want things, they demand for more faster and quicker interactions. So now Facebook actually back then when they create is React, they come out with these particular solutions as a way to now provide this rich web interactive applications or this client-side applications, which is now load things much faster and now provide all of this interactivity to the user at once. So because of this, we have now is several rendering modes. So you have now the server-side rendering mode, which is the traditional one, okay? We also have the client-side rendering, which is now The browse, anytime the user wants to navigate to the product list, so the server is going to send now is the HTML, CSS, and JavaScript to that. The browser receive that HTML as well as the necessary JavaScript to actually load the application initially, show an initial screen, a loading screen, while in the background hurry up everything else to download all the necessary assets. Once that is done, the page now becomes responsive and interactive, visible and interactive. So because of this, its impact is search engine optimizations, but this is great for back office or game applications or any other application that doesn't require CEO or SEO, sorry. But for those that needs that, then you have now all of these hybrid rendering models. So you have now, of course, the server-side rendering. That's not hybrid, but we have now is the stale while revalidate. That's one of them, and this is very specific to the React ecosystem, as well as the Vue. If you may wonder, we also have is we also have is the incremental stale while the incremental. Yeah, we have is the incremental state, incremental rendering as well. Incremental static regeneration as well. So for example, in the case of this, incremental static regeneration. So update static content without rebuilding the entire site. Redux server load by serving pre-render static page for most requests. Ensure proper cache control. Interesting. Cache control. Headers are automatically added to pages. Handle large amount of content without long next build time. Here's a minimal example of that. So the thing here is that all of these specific rendering modes, so you have now the incremental static regenerations or these stale while revalidation, client-side rendering, as well as server-side rendering. All of this is just because those particularly challenge when it comes to describe UI in a way that is much more easy and engaging to the user. Now we come up with this particularly challenge. So in any case, as a way to understand now the role of Redux or RTKey here, this is something that now the Redux or this RTKey, the problem that it wants to solve is that because anytime you want to define is this a specific state, all right, and when you need to define is the update logic, it requires you a lot of ceremony that you have to go through, especially because it is influenced in the Flux architecture, okay, that we need to actually do that by hand. So anytime you want to define is a new state, you also need to define is the actions, which is an option, as well as the in a particular file, as well as the reducer in a particular file, and also then is define is the initial state, all right, and then it's when you're going to now dispatch those actions whenever you see fit. So Redux RTKey actually simplify those particular process in just one single function. And also, when you want to now add more functionality to your Redux, because this is a great tool, especially for time travel debugging and yeah, most likely for time travel debugging or adding some middlewares to that. A lot of the time is something that it requires you to go to actually do that. So adding middlewares right now is something that is more and more easy to do. And the other challenge is especially when we need to provide some TypeScript support. So actually trying to provide some TypeScript in Redux is something that it becomes quite cumbersome. It requires you to use some arcane TypeScript features, and then you need to keep up the pace with the development phase. So this is the three main problems that Redux Toolkit actually solve. Of course, there are other lightweight implementations of Redux. So you have Sunstand and that kind of thing, which is quite great, all right? But I will argue that if you want to develop battle test applications for in a particular industry, let's say you want to do that for the oil and gas, so the energy industry or the healthcare industry or the real estate industry, a lot of the time it is good to keep up the pace of in use is some of these well battle tests without trying to change that much. The natural step is that we eventually going to create is all of this as software, okay? We eventually needs to create is a software we eventually with the software we eventually need to create is interesting. Yeah, with the software, we eventually need to update is our application with the new patterns. But again, as much as possible, stick with tools that are popular, mature, and that has a large community that support it. So in any case, so far this course is pretty short. It's pretty straightforward. The introduction, which is something that we already described, the Redux toolkits and the type hooks. And today we're gonna describe briefly is how we can create a slide, what is the problem that solved, as well as the actions, and dive deep into the reducers. So what is the problem that reducer in RTKey actually solve, right? So because after all, we looked at the create slides actually simplifies and automates the process of by providing is an initial state as well as the reducer and is in the name slice, okay, it will now behind the scenes create you actions, type actions, reducers, and the state for that. So this is something quite interesting, all right? We also see how can we now work with other models, which is part of which is one of the goal of this course, is that we're gonna see how can we work with different models, as well as how can we use TypeScript behind the scenes, and also is that how can we now use the Redux toolkit as a way to now perform these async operations. So the other is create actions, right? Yeah, the other is create actions. So here in create actions, as you can see, what it does is, so the problem that it solves is, well, automatically create is the actions, which is a particular object that contains the type and the payload, and also the type for that, which is quite interesting. We also look at what is doing behind the scenes, how that works, and how you can migrate from one particular reducers that to use now is create actions, right? So as you can see, this is quite interesting, straightforward. We started to also use is some of this return type like that, okay? And then we look now at the reducers. So the problem that these reducers are solving is quite a little, is a couple problems nested inside of that. First is that not only simplify the creation of our reducers, okay, by avoiding us to create all of these reducer on foot, which is our Swift statements and define all of these particular cases, but also it provides a better TypeScript support. And when we need to actually update the state, which is that's the things that allow this reducer, okay, we do that in a mutable syntax line. What does it mean by that? Because this reducer, this create reducer function, this create reducer functions behind the scenes is using now something called that is Immer. So if you want to use now your reducer, okay, which is now this function that is going to take is the initial state, and it takes also the builder that is use a notation, the builder callback notations allows to define now handlers for action specific or for specific actions types. So you can now not only is allows to define is their cases, which is using the switch and all that kind of things, but also provide some other functionality here. So like match case, so add a match case and add a default case. So why this is important? Because instead of us having to update the state in an immutable way, and to do that, back in the old days, we have to use is the object.assign. That what it does is to create is a new object from the scratch, okay, or have access or allowed to a particular object to have access to the prototype of another object, okay. In our particular case, this builder callback notations, instead of us having to manually define is the state update in an immutable way by hand per level, which is something that you have to do, especially if you define is more nested objects, all right. So the thing here is that instead of us having to do that, for example, let me see, there is like this, all right, and the more nested values that you have to do, your update logic becomes is quite verbose. So by using this Immer here, anytime you want to update that particular state, they say, good, let me handle that for you. So we're gonna use Immer here, where when you need to define some of these most common use cases, for example, like add a case to your reducer, or match a case, or add the default state inside of one of these callback builder notation, instead of you having to manually create a new state or handle the immutability by yourself, okay? Which means that anytime you want to create a new state, you have to, per each level, you need to create is the, or recreate is the object itself, and then identify is the proper property to update that value. So the more nested the property is, the more you have to do that per level, that immutability. So Immer says, hey, I'm gonna, instead of you having to do that, because it can become quite error prone, and also make the update logic quite verbose. So I'm going to now provide you a particular mechanism where you're gonna, in this draft, update your object, okay? And then I'm going to, after you modify the draft, and after the draft is done, then I'm going to generate is now a new state for that you can use. A new immutable state. That's quite interesting. That's very, very, very interesting for that. So again, it's abstract you the logic of using Immer. It's abstract you the real work that you have to do anytime you need to create a new state. As part of that, state action is reducers. And you may wonder why we need to create a new state. Well, because at the end of the day, this particular approach has proven to be a good one that is avoiding to have any side effects. Okay, so we make our applications pure. We make the data pure, which is great. And I don't know why they don't have this kind of thing. That's interesting. Except reducers and immutable updates. Exactly. Reducers can only make copies of the original values and then can mutate the copies. But okay, this is actually explaining as this reducers. Oh, the Redux fundamental. Okay. Yeah, the Redux fundamental. Yeah. Yeah, okay. But in any case, the create reducer, okay, behind the scenes, as I mentioned here, is using is this builder callback notation as a way to now provide this compelling functions for us to add a case, add a matcher, add a default case, and inside of this is when we're going to use is the create actions that we defined previously, right? Followed by the callback functions of what we want to actually update. We're gonna receive is the state and then actions, and then do something with that particular things. So exactly the direct state mutations. So or you either is mutate the state, okay, providing by the, so when you define your state, when you define your case, or you either define your state, or you either mutate that state, or you return a new state of that, right? So for example, like this. So when you return is a new when you mutate the state inside of that builder notation, what it's doing is behind the scene is actually is ensure that that generation of new states by using its Immer for that. So because of they using its Immer, you either or return a new state, for example like this, or you just mutate the state for that. But you must only do once. So this case reducer both mutated binding states and the new state. And that's what you're going to have is some sort of problems here. So briefly describe here Immer, okay? So Immer actually is making you to work with immutable states in a more compelling way. This was a library created in Germany, I think it is. Shout out to German people. Yeah, shout out to the builder of this completely. Because yeah, Immer is solving this these common problems, especially when you need to mutate your state. It's gonna detect accidental mutation and throw in errors. So why this is important of understanding is the immutability, right? And I think this is quite interesting as a way as we dive deep into this. So immutability, okay? So front end master, right? There you got it. Oh, it's because like this. There you got it. There you got it. What is this part? This is the immutability in Cal. Okay. Let me see the core structure here. Function purity, argument adapter, point free, closures, mutations, compositions, declarative data flow, as immutability. Exactly. So let's briefly see what immutability is. You are not going to see what I'm gonna do because I don't want to receive any red flags. I already received one, so no thank you. Yeah, I already received one, so no thank you. And let's get into this. No. Of course. Says one. Remember me. Oh. Immutability. What is
Immutability. Now this is a topic that gets glossed over a lot, so we want to make sure we pay a close immutability. Now this is a topic that gets glossed over a lot.
Get closer. Get closer. Get closer. What in the heck? Get closer. Victoria's Secret. What? Why get closer? Meaning. What in the F doesn't mean that? Hey, get closer. Yeah, what does it mean this? Get closer. Meaning. And I want to see as I get closer, urban dictionary word. So that, oh my god. To get wasted and become very talkative. What? What? A state of extreme highness in which one's eyes are quite shiny and appear glossy. Okay. To state of extreme highness. Oh, stop. Glossy, in which eyes are quite shiny and appear glossy. Oh, urban dictionary. You got a glossy, gloss. Dude, Dylan smokes some quality dank and got a hell gloss on Friday. Oh my god. Oh crap. Okay. To provide an explanation for a word or phrase. In the school, oh, get glows. Interesting. Get glows meaning. Yeah, get the glows. In Spanish. Okay. Please be my guest. Yeah, it's like glows. Brillo. Glows, brillo. That's interesting. That's very, very interesting. Very, very interesting. Okay, glows. Now this is a topic that get glows over a lot. Interesting. Get glows over a lot. Okay.
So we want to make sure we pay a close attention to this, and in particular, immutability. Now this is a topic that gets glossed over a lot.
Get gloss over. Gloss over. Oh my god, gloss over. Gloss over. Gloss over. To treat or describe something, such as serious problem or error, as if it were not important. Get gloss over. Gloss over. Because gloss, it means brillo. Como si no brillara mucho. Oh, okay. Get gloss over. Yeah, this is something that is true. This is something that is this is something that glows over a lot. This is the topic that get glows over a lot. Exactly.
So we want to make sure we pay a close attention to this. And in particular, one of the things that I get kind of frustrated about is that when people throw around this word, they could mean one of at least two different things, but they're not very often very clear about what is being discussed. So let's make sure we understand first why immutability is important, but then what kind of immutability are we talking about? So immutability is the idea, obviously the word implies that something isn't going to change, but that doesn't fully encompass what we're talking about. It's not just that things don't change, it's that things don't change unexpectedly. There is obviously in our programs a lot of
things don't change unexpectedly. It's about control.
State change. That is the whole point of our programs, is for state to change over time. And state change being the point, you don't want to stop that from happening. There's really no such thing as like making an immutable program, because that program wouldn't have any point. There'd be no reason for that program to exist if nothing could change. So really this idea of immutability it's broken in our brains, or it's miswired in our brains when we think about it in terms of things that can't change. That's not really the point. Really the point of immutability is that change that needs to occur needs to be intentional. It shouldn't be accidental.
Okay. Needs to be changed. Context. Needs to be changed. Needs to be changed intentionally. It shouldn't be accidental.
It shouldn't be happening without us being aware, happening at different times, creating race conditions, all those sorts of things. So immutability is this concept of how do we control mutation? How do we control change? And I said there's two different kinds of immutability that we want to pay attention to. So the first of those is assignment immutability. Assignment immutability is the idea that when you assign something to a variable or to a property, that it is no longer allowed to be reassigned to some other value. And this is often, a big deal is often made of this. In fact, you'll know we talked earlier in the course about the const keyword. This idea that if I create a variable that can't be reassigned to, that I've somehow prevented myself from having bugs. So let's dig into that. Let's talk about assignment immutability. If I declare base price, as we are on line 1, with a var declaration, and then shipping cost with a const declaration, they are both variables. Variable is sort of a weird word here because for a const it can't vary. But it is a placeholder for a value. It is a symbolic representation in memory. So that's why we call it still a variable. Except there's a difference between these two, which is how they're going to handle reassignment. With a var declared, or even a let, if you choose to reassign it to a different value later, which is what's happening on line 6, no problem, of course, everything works fine. But if you try to reassign something that is declared as a const, you get an error saying that's not allowed. It's not allowed for you to change or to reassign. As a matter of fact, we really need to get into the word change, because the word change implies that we're changing something about the value itself, and we're not really changing the value. Base price is not being, its value is not being changed, its value is being reassigned. We're creating a whole new value with that plus operation, the value 94.99, and we're assigning that new value into base price.
So we are telling now, hey, in memory, I want you to now have this new value for that. So that makes a lot of sense when you're describing is this the ability to keep track state change of immutability. So immutability is, yeah, I get it why this concept is closed over a lot.
The reason why that's important is that there are values which can be mutated. A number, for example, can't be mutated. You can't ever change 3.14 into anything other than 3.14. It just is that. Same thing with strings. You can't take the string hello world and modify one of the characters inside of that string. That isn't a thing that you can do. Those values are sort of inherently immutable. They are primitive values that can't really be changed. So we're not changing the value, we're reassigning the value in base price. We're creating a new value from an operation and assigning it into base price. And when we try to do the same thing on line 10, we get an error saying, no, that's not allowed for you to reassign. That's what the error means. You can't assign to a const variable other than at the first time. And by the way, just a little note on const, this is sometimes overlooked. You cannot declare a const without assigning it a value. So you can't say like const shipping cost and then later in that same block of code give it its first assignment. Because actually that would be observing it in two different value states. One where it was undefined and then one where it was defined to a value. And they took great pains to prevent you from observing a variable in this sort of two-state or a constant in this two-state situation. Matter of fact, if you've heard, you may have read a blog post about something, it's called the temporal dead zone.
The temporal dead zone, makes sense. It's like they have creating, okay. Exactly, especially the temporal dead zone. When you define a variable, when you define a variable without any value, or when you declare a variable and then you assign that.
And temporal dead zone is all about preventing us from seeing a const ever be in this weird in-between or this gray area state where it was undefined and now it's been defined to a variable. So we've taken great pains to ensure that you have to assign it that value and then you can't reassign it later. Now, I've heard many explanations for why we should use a const in our programs. And as a matter of fact, some of the most vehement support for the const keyword comes from the functional programming community that does JavaScript programming. They feel const in great pains to ensure that you have to assign it that value and then you can't reassign it later. Now, I've heard many explanations for why we should use a const in our programs. And as a matter of fact, some of the most vehement support for the const keyword comes from the functional programming community that does JavaScript programming. They feel like this is a big boon, it's a big improvement to the language to have a const keyword. I'm not convinced that it really does provide the value that it assumes to provide, and I want to dig into why I'm not really convinced about that. So if we think about this code, there's another way of avoiding this problem of assignment or reassignment, and this is actually how functional programmers prefer to work. If you think about the argument that a functional programmer makes, which says, I don't want my variable to get reassigned accidentally, so I always declare everything with const. That's the typical line, that's the typical statement. But then they don't actually assign many variables anyway. most of the time, I mean, this is called functional programming for a reason, because most of the time, we're not doing assignment statements. Most of the time, values are being passed to functions and coming back from other functions. So if you see what's happening here, I can compute the new base price or the new shipping cost by simply passing the existing value to a function, computing it, and having that return value come back. And I can or cannot decide to assign that value to some variable. But those are separate questions. The computation of a new value versus the assignment to another variable, they're separate questions.
Exactly.
And as a matter of fact, most functional programming...
Not only they're separate questions, is that they are separate concerns. It's like, wait, what? No, come on. Okay. Yeah, is that there are not only two separate concerns, all right, about the immutability, and especially is assignment and generation of new state for that.
Programmers tell you, try to avoid assignment at all costs. You'll see long strings of composition where a function goes to another function and then it goes here and here and here and here and here, because heaven forbid we assign it to a variable temporarily and then use that variable later. We want to avoid that at all costs. So one of the questions that comes up in my mind when I hear a functional programmer say, no, const, you should absolutely only use const, is, do you really even care that much about const? You don't even like to do assignments if you're a functional programmer. So that's one of the reasons why I sort of suspect of, or I'm sort of in doubt of whether or not it's really bringing that much benefit to the table. Here's another reason why I'm kind of concerned about the proliferation of const within our language. There is a lot of baggage that comes with the const keyword. Certainly this is not a new invention for the JavaScript language. Const was added to languages decades ago. And if you look even on a site like Stack Overflow and do a search for questions about a const keyword, you can find thousands and thousands of questions and problems that people have had with this keyword in basically every language that it's ever been added to. And I think one of the root reasons, if I'm trying to approach that question as an educator, as somebody who tries to understand what problems people who are learning things have and what they need to do to get over those problems, when I look at it from that lens, I think the real problem comes down to the English language being difficult to parse alongside of programming language. When we say the word constant, a lot of us mean something that doesn't change. When we say that in sort of everyday language, if we said the temperature has been constant today, it hasn't changed today. That's what we mean. So we're implying something that doesn't change, and that's this gray area. What thing is it that's not changing with a constant? So if I point const at a value, if I point a const declaration at a value that itself cannot change, like 6.5, that's sort of a moot point. The value can't change anyway, so it doesn't matter. But if I point it at a thing that can change, for example, an array, now all of a sudden we see that there is a nuance difference that is really important. It's nuanced, but actually it should be the whole thing. Because the question is whether or not we care about reassigning a variable, or whether we care about a value that could be mutated having been changed. For example, adding or removing an element from an array, or reassigning one of the properties of an object. Those are mutations to a value that are possible with certain value types, like arrays and objects, which basically aren't possible with a number or a string. So when we use a const with something primitive that isn't already changeable, it's not such a big deal. The nuance doesn't present itself. But when you start, for example, assigning functions to const, like we're doing here on line 3, functions are actually objects, and they can have properties on them. That isn't typically done that much, but you can use a function as an object, and of course that means the value can be mutated. And even worse, when you use const with real objects or with real arrays, you create this confusion, I think, in people, where they think in their mind initially, that is a value that isn't going to change, when actually what the const keyword is saying is it's an assignment that isn't going to change. So if I create an array and I assign it with a const declaration, and then later that value changes, the most likely outcome is that the reader is going to be confused. Certainly you can learn to get along with the const keyword. Certainly you can learn that keyword, you can learn its mechanics, you can use it so often that that becomes not a problem for you. But the default reaction for programmers seems to be to get it confused, which is why there's so many questions on Stack Overflow about it. People saying, well, I declared it with a constant and it changed, or it wasn't declared with a constant, it didn't change. I mean, it just creates perpetual confusion. So much so that some programming language communities had so much trouble with it that the language itself, namely I'm talking about Java here, they basically deprecated the const keyword and introduced a new keyword in its place called final. because const had this English language baggage attached to it that said it's a constant, it's a thing that's not going to change. And now we're saying final sort of implies it's the final assignment of this variable.
Okay.
I guess that's helped the Java community. I'm certainly not a Java programmer, but they had to make that change because people were confused by it.
That's quite interesting that the Java community has this final keyword. Oh my God. Hey, who? Why? Oh my God. That's okay. Final keyword in Java. Oh my God. Final keyword in Java is to say, hey, this is the final value that this. Oh my God. Final, double P and that kind of thing. Which is the final variable. So you can mutate that. It's used as a non-access modifier applicable only to variables, a method, or class. It is used to restrict a user in Java to create constant variables, prevent methods overriding, and prevent inheritance. The final keyword is used to define constants to prevent inheritance in Java. To understand how and when to use final effectively, the Java programming course offer a in-depth explanation of practical application of the final keyword like this. That's quite interesting, my friend. That's very, very
We're going to talk about multi-dimensional arrays in Java. Let's take a look at this example. Here we have created a 2D array. We have used two square brackets and we have initialized this 2D array with elements as 1, 2, 3, 4, 5, 6. Now if we wish to traverse this array, we use arr.length to find how many rows this array has. Then we use arri.length to find how many columns individual rows have. So this loop is going to run 2 times because there are 2 rows, and this loop is going to run 3 times for every row because every row has 3 items. And inside this loop we have print statement, so we are going to get the output as 1, 2, 3, 4, 5, 6. This program, if you take a closer look at it, it looks different from C++ program or C++ style of creating multi-dimensional arrays. Here we have actually an array of objects. This 2-dimensional array is actually array of 2 array objects. And these individual objects are arrays and they have 3 elements. We find...
So there it is. That's quite interesting that the final keyword in Java was defined for that. It's like, and there is and there is something here that is missing, especially in the English language as well as the Spanish, right? Or Latin language, when they say constant. Esto es una constante, no cambia. And that's one of the reasons why it is important to understand the context. What is this context, and where this context is applicable? Because all of these particular words, all of this way to describe something in the real world, they work in a particular context, right? So for example, life, you say life, but life, so far, we have encountered that it can only happen in this given condition. At least the mammal life, all right? And if you go down deep, the more down deep you go, for example, is life for insects or bacteria or protozoals, perhaps the more other contexts it can happen. And I think this is quite interesting. So if you take a look now at something that is, for example, in Yeah, if we take a look now at, for example, at the uh, Japanese in Latin America, again, that is not that helpful. The Japanese is not helpful if you learn Japanese, which is great, good. It's helpful in Japan or in those countries that are capable to understand and talk in Japan. But in Latin, it's like, what in the F is this? It's like, ¿qué carajo? ¿Qué poronga me estás hablando, boludo? Es. So this is something interesting. And as a way to explain now is the immutability. And what immutability means in this context. It means that it's not the ability to not change stuff, right? Or not the ability to make things constant. It's in fact is the ability to make change intentionally, that we can keep track those state change. That's what immutability means in the software community. And they have now this subtle difference between is the assignment, which is something that you define here, okay? The assignment,
Immutability us from seeing
the assignment,
really accidentally.
Yeah, you define
Community. The temp would give, that's what the error really be changed.
the
One for,
assignments.
we're not really changing the sign. As a matter of fact, const, you get an error set value later. Except there's a difference between placeholder for a value. It is a symbolic
There is a difference between an assignment.
representation in memory. So that's why we call it still a variable. Except there's a difference between these two, which is how they're going to handle reassignment. With a var declared or even a let, if
It's about assignment.
here's another reason why I'm kind of concerned about the proliferation of const within our language. There is a lot of baggage that comes with the const keyword. Certainly this is not a new invention for the JavaScript language. Const was added to languages decades ago. And if you look even on a site like Stack Overflow and do a search for questions about a const keyword, you can find thousands and thousands of questions and problems that people have had with this keyword in basically every language that it's ever been added to. And I think one of the root reasons, if I'm trying to approach that question as an educator, as somebody who tries to understand what problems people who are learning things have and what they need to do to get over those problems, when I look at it from that lens, I think the real problem comes down to the English language being difficult to parse alongside of programming language. When we say the word constant, a lot of us mean something that doesn't change. When we say that in sort of everyday language, if we said the temperature has been constant today, it hasn't changed today. That's what we mean. So we're implying something that doesn't change, and that's this gray area. What thing is it that's not changing with a constant? So if I point const at a value, if I point a const declaration at a value that itself cannot change, like 6.5, that's sort of a moot point. The value can't change anyway, so it doesn't matter. But if I point it at a thing that can change, for example, an array, now all of a sudden we see that there is a nuance difference that is really important. It's nuanced, but actually it should be the whole thing. Because the question is whether or not we care about reassigning a variable or whether we care about a value that could be mutated having been changed. For example, adding or removing an element from an array or reassigning one of the properties of an object. Those are mutations to a value that are possible with certain value types like arrays and objects, which basically aren't possible with a number or a string. So when we use a const with something primitive that isn't already changeable, it's not such a big deal. The nuance doesn't present itself. But when you start, for example, assigning functions to const, like we're doing here on line 3, functions are actually objects and they can have properties on them. That isn't typically done that much, but you can use a function as an object, and of course that means the value can be mutated. And even worse, when you use const with real objects or with real arrays, you create this confusion, I think, in people where they think in their mind initially, that is a value that isn't going to change, when actually what the const keyword is saying is it's an assignment that isn't going to change. So if I create an array and I assign it with a const declaration, and then later that value changes, the most likely outcome is that the reader is going to be confused. Certainly you can learn to get along with the const keyword. Certainly you can learn that keyword, you can learn its mechanics, you can use it so often that that becomes not a problem for you. But the default reaction for programmers seems to be to get it confused, which is why there's so many questions on Stack Overflow about it. people saying, well, I declared it with a constant and it changed, or it wasn't declared with a constant, it didn't change. I mean, it just creates perpetual confusion. So much so that some programming language communities had so much trouble with it that the language itself, namely I'm talking about Java here, they basically deprecated the const keyword and introduced a new keyword in its place called final. Because const had this English language baggage attached to it that said it's a constant, it's a thing that's not going to change. And now we're saying final sort of implies it's the final assignment of this variable. I guess that's helped the Java community. I'm certainly not a Java programmer, but they had to make that change because people were confused by it. And I've set up this entire course in the context of we want to communicate better with our code. Why would we use a feature which has long historical precedent for confusing people? So that's where the real trouble that I have comes from. It starts out already in the negative, if you will. And with any programming language feature, with any framework feature, the question that needs to be asked is, does that thing carry its own weight? Does it have enough benefit to overcome any potential downsides that it may present? Most of the time, I think we'd say that would be true. But with the const keyword, my claim is it doesn't really carry its own weight. If it's going to trip people up, if it's likely to, especially the new readers of a piece of code or people that aren't yet familiar with the thing, if it's going to have that strong potential to trip people up, that strong decades-long precedent for tripping people up, then it ought to provide a really substantial benefit to our program to justify its inclusion. And the claims of its benefit are, I think, at best weak. So for example, in this slide, we see a const declaration on line 2, another const declaration on line 3. And then, of course, line 8, since it's named that way, it sort of implies it's doing a side effect. It's writing to a database or changing a record in the DOM or who knows what it's doing. But the point that I'm making is that this is a relatively short block of code. It's only 7 lines of code inside of the curly brace blocks. We're told many times that we should keep our blocks short, that we shouldn't be writing hundreds or thousands of line-long blocks because it's hard for the reader to understand things. My own personal kind of a style guide, if you will, or what I try to keep, is I try to keep no block, no function larger than what I can see on the screen at any given time. And at my general zoom level, that's about 20, maybe 25 lines at most. So if it's longer than that, I'm immediately thinking to myself, I should be refactoring this thing. I should be trying to break it down into 10, 15, 20 line at most. I shouldn't be having 100-line long blocks. And I'll be honest with you, you can see a lot of my code if you go to my GitHub that breaks that rule. So I'm not always perfect. In fact, I'm often not perfect at that. But it's a general guide for myself that I don't want to have these long, long blocks that are hard to read. So if you're following that sort of thing, if you're following what the general best practice is to have a short block, we need to understand that the idea of assignment is inherently related to the idea of lexical scope. The idea of assigning to a variable is inextricably linked to the idea that that variable belongs to a particular scope. When we do const shipping cost on line 2, we have created a variable that exists only for the next 6 lines of code. It does not exist anywhere else in the program. And that means that nowhere else in the program could possibly reassign it. We have a short block of code, and we have only a few lines of code that could possibly do the reassignment. So the typical argument is, oh, well, const signals intent. It tells the developer that's reading your code, you don't have to worry, it won't get reassigned later in the code. But if we're following best practice, that's not very many lines of code that it's asserting anything about anyway. It's not as if we have tens of thousands of lines of code that we couldn't possibly as a human juggle. Right here we have 6 other lines. And there's another way to say to the reader of your code, I'm not going to reassign a thing, and it's to simply just not reassign it. As a matter of fact, if you're doing functional programming, don't assign at all. As little as possible, do assignments. So I'm not sure that the const keyword is actually providing all that much benefit, even in this best case scenario where you're saying to the developer, hey, listen, I'm not going to reassign it, because most of the lines that it could be reassigned are already clearly visible to you. And you can see that it's not being reassigned. In these particular cases, since we're inside of a block, my preference is to use the let keyword. And I use the var keyword at the function level scope rather than the let because it says to readers and has for 23 years, this variable belongs to the entire function. So maybe assignment to readers and have particular cases, since we're inside of a block, my preference is to use the let keyword. And I use the var keyword at the function level scope rather than the let because it says to readers and has for 23 years, this variable belongs to the entire function.
That's right.
So maybe assignment immutability isn't such a big deal. Maybe it isn't the problem that we really ought to be concerning ourselves with. But there is a much bigger deal that I think we should be concerning ourselves with. That's the question of value immutability. Because unlike assignments, which are lexical,
There you go, It's like we're talking about immutability, and that's the confusion that actually I experienced, and that's why I didn't get the job that I want or that I need to back in that moment. When I say, what is the sort of difference between cons, and what happened when I update the value of a cons, all right? And that's something that was troublesome to me. Because it's like, it's supposed to be constant in terms of values, but it's not, because it's constant in terms of assignment. It means that you can, so for primitive, there is no problem, because after all, what you're gonna do is just assign. You're not mutating that. It's quite clear when you use primitive, right? But when you start to use objects, functions, an array, then you start to see, okay, how this thing, what is the mechanism of how this cons works? Does it mean that are we changing is the value of this identifier, okay? Or it means that we don't change the value of that identifier. You know what I mean? So that's when things started to get tricky. Very, very tricky and interesting.
scoped by their literal definition. They are lexically scoped to generally a small portion of our program. Values, especially values that are passed by reference, are completely portable. They can go anywhere in the program and even beyond the program to other third-party code that is included in running. So if you take an array that has some numbers in it and you pass it somewhere else, you have to be asking yourself the question, what is going to happen to that value? Value immutability is a much more important question. If we were trying to come up with some sort of rating system here, I'd say 99% of the problems that we face come from a value being mutated in a way that we didn't expect. There's some global state object that has 1,500 properties on it, and somewhere some weird obscure piece of code changed 2 or 3 of those properties in a way that we didn't expect. That's a value mutation, and it has absolutely nothing to do with whether you use the const keyword or not. So value immutability is the big problem. 99% of the problem comes from value immutability, or value mutability, rather, and only 1% of the time at best does it ever come from reassignment. As a matter of fact, and I'm being completely honest with you, as a matter of fact, based upon my own sort of introspection about my processes and code, never once, not a single time, has there ever been a case where one of the bugs that I was trying to fix was, oops, I reassigned a thing that I wasn't planning to assign. That's never once been the problem that I've had. And I'm not saying that that's never been a problem for anybody. I'm sure that const exists because somebody somewhere reassigned a thing. But in 25 years of programming experience across a variety of languages, I've written, I can't even count how many bugs. I'm way better than all of you at writing bugs. I'm good at it. And all the bugs that I've written, never once has the problem been, oops, I meant to leave X alone. And instead I should have written Y or something. That just isn't generally the problem that I face. And so I'm skeptical as to whether or not that assignment problem is really so widespread. And I think we're not getting the proper attention on the value mutability problem. Did you have a question?
I was just saying the only example I've ever seen is like doing a for loop and accidentally reassigning I when you use two for loops or whatever.
That's a great point, right? So like, yes, you could definitely accidentally have a variable updated inside of a for loop and then it throws the for loop off. Some people do that on purpose. They'll like write for loops where they skip or go back, and I've written code like that before, and that's always been a pain in the neck to manage and debug later. It's always been a terrible idea. But I'm glad you bring up this point because that's an example where it theoretically could be a problem, and guess what? Const doesn't solve that problem for us because you, by definition, have to update that incrementer in your for loop. So you can't declare it with a const anyway. So yes, it's a problem, but it's not a problem that the const keyword is solving for us. Let's take a look at some examples of value mutability and how we can address this question of value mutability. So here I'm creating an order details object, and I'm conditionally adding some stuff in. So I need for this thing to be able to be mutated because I need to run some other conditions and maybe update some properties or things like I am doing on line 7 through 9. And then line 11, I pass that object, and because it's an object that's passed by reference, I pass that object by reference into this process order function. Now, do any of us have any idea what process order is doing? Well, we don't see it here. It's not local, so the answer is no. We don't know what process order is doing. Can we go and look at all the code in process order and figure out? Sure.
Yes.
But if there was something in this block after process order that was relying upon order details, we now automatically would have to have the suspicion, if we're paying attention, we have to have the suspicion, did something change about the order details object? And if that isn't our intuition to ask, then it is almost certainly going to be the source of a bug at some point. One of the things that we do as functional programmers is try to predict where the bugs are going to be and avoid them before they occur by using patterns where they can't happen. And passing a value by reference where somebody could accidentally or intentionally change a thing in a way that we're not expecting is like putting up a giant neon sign that says, please create a bug here that I haven't planned for. And this is why functional programmers take this so seriously. This is why immutability is one of the most critical topics, and I think often undercovered topics in all of functional programming. Because values get passed everywhere.
This is something interesting that he mentioned. And one of the problems that actually are solving or trying to address functional programming, especially if you have an object that is representing is user data, personal or sensitive data, okay? And by sensitive data we say is like financial data or health records, debit and credit cards, just to mention a few ones, okay? And if you are, for example, is mutating or modifying is that data in multiple places, that is likely to, for new developers, to say what in the F is going on here. So this is untangling all of these things. So instead of actually mutating that object, okay, and that's a real concern from us as a programmers and developers, is to say, all right, now that we get that, okay, so now that we get that, what is the TLDR of all of this, okay? How can we address that particular problem? You know, you're starting to have now more interesting problems, more better problems. And one of the things that functional programmers say is like, please don't ever use is, so please don't ever mutate is the state of the program. Instead, generate a new state out of that. Makes sense.
It's arrays and objects and functions all over the place. And we should be asking ourselves every time we pass it, how do I know that that isn't going to change in a way that is going to create a bug in my program? When I pass the number 42 or the number or the string hello world, I'm not worried because I know the language already protects me. But when I pass an object in an array, I don't have that same level of guarantee. So even without going and looking at the process order function, I'm going to make an assertion that the reader of this code could benefit from some sort of process or convention that would allow them to know that they can trust that order details is not going to get changed. So what do we need? Your instinct might be to say, because we're talking about immutability, aha, we need an immutable data structure. No, we don't. Because what we need right now is we just need to say that this value is read-only. And that is a different sort of a claim than asking for it to be an immutable data structure. And I know that seems counterintuitive, but hang with me because we're going to talk about what immutable data structures are about. And I'm going to say, right now we're focused only on the claim, could I say that this thing is read-only? That it cannot be mutated in any way. Because I think a lot of times when people think, oh, I guess I need an immutable data structure, actually what they need is just a read-only data structure. A data structure that can be read but cannot be written to. And those are different than immutable data structures. So it turns out, it's built into the language, there is a way to have a read-only data structure, pretty simple, and that is to call object.freeze. Object.freeze, as you see on line 11, is telling that object, you should change all of your properties to have the read-only attribute on them so that none of them can be changed. The object can't have properties added. It can't have properties deleted. It is, however, only shallow. So be aware that if you had nested objects of nested objects of nested objects of arrays, you would have to freeze each one of those levels to get that same level of guarantee. But in our simple case, where we have a simple single-layer object, a simple call to object.freeze gives us the guarantee.
Gives the guarantee that this.
But I'm actually going to make a slightly even different claim.
Only.
I literally don't care if object.freeze actually does what it's supposed to do. I mean, it could be like an empty, hollow polyfill. The real point is that I am communicating something to the reader of the code at this point. It is less important to me that it actually be read-only, and more important to me that the reader be able to know I'm saying you don't have to worry about this thing changing. As a matter of fact, it'd be nice if the language gave us some sort of syntactic facility for that. Maybe an operator when we make an object or when we pass it or something. You know, they're not ever going to probably add something like this, but it's a harebrained idea. But it'd be nice if there was even a lighter weight way than saying object.freeze. But basically what I want is an annotation that tells the reader, you don't have to worry, it's not going to be modified. It's read-only.
It's read-only.
You don't have to worry about it being mutated in some way that you don't expect. Now, the good part is that object freeze does actually do what it's supposed to do. So it gives us not only the signal to it, but it enforces it from a runtime perspective. That if process order were to try to do something that it shouldn't, the whole program's going to blow up and an exception is going to be thrown. Mm-hmm. Now, the reason why I say I don't actually care about that part is because it is vanishingly rare that something like that, like trying to reassign to a property that was actually set as read-only, it's rare that that's been wrapped in some try-catch and gracefully surfaced to the user as a, oops, something went wrong. Because if that occurs, if you pass in a read-only data structure to process order, and process order is in the habit of wanting to mutate the thing, then you have a fatal, unrecoverable bug in your program. It's the kind of thing that we'd like a linter to catch for us. And maybe depending on what kind of, programming language, or if you're using a TypeScript or something like that, maybe you can get a linter, a static checker, to sort of tell you about that problem. But if it passed in as a read-only and then process order tried to catch it, that's going to create a fatal error condition, and you, the developer, are going to fix it. What I'm really concerned about is when we don't have those fatal errors, but we have those subtle, crappy bugs that are really, really hard to debug. The user is still able to check out, but it charged them $1 extra on the order than it should have, and nobody can figure out where that extra $1 came from. Those are the terrible bugs, aren't they? They're the ones where there wasn't a fatal crash, but it was still a bug, and it's really hard to reproduce the conditions for that. And one of the ways that we avoid those sorts of things is by telling the reader of this code, or at least, whether we avoid the bug or not, at least make it easier to diagnose, is we tell the reader, you don't have to worry, the object didn't change at this point. It's not going to change.
This is something interesting because as we move on in the industry, and we, at the end of the day, we don't own the code that we wrote because we don't have any ownership on that code unless you have that, right? You have is a responsibility to build a particular application that follows certain rules and guidelines and that kind of thing. So, over the couple decades, all of these people that have worked in all of this language. So you have Kyle Simpson, you have the creator of JavaScript, which is Brendan H., and as well as other developers that have contributed to the JavaScript ecosystem. Now they have realized and they have learned from their own mistakes. I think I will argue that might be the way of how humans learn from our mistake. And especially in an environment that requires you to solve things on the fly. Okay, hey, does it work? Good. Next one, and then you move on. It also is because the nature of not only the market, but the nature of solving problems based on priorities, right? So a good example of that is, if you were in 500 years, if you live in, for example, Latam, if you live in Europe 500 years ago in a rural area, it is very, very hard for you to think about problems like existentialism. You know, again, because you just worry about your closest immediate problem. That is, hey, do I have enough crops to satisfy my own family needs? And then I can sell my crops to other communities. Uh, but this is the natural step of how can we solve problems, and most of the time we have to learn from our mistakes and then act accordingly. Um, and so in this case, the JavaScript community, the developer community, in whether it's in Java, in JavaScript, but it's in this case in Java, they recognize is that mutating stuff, especially in an object, or mutating things, is something that is quite cumbersome. So, for example, if you, a good example is if you're holding your keys. So, if your keys are anytime, so if you don't have a particular protocol, a particular way of letting your key in the same place, you will never find your keys there. So in my case, I left my keys in the same place most of the time. I also changed where I left them. But if you do that in a way that is, you can track when that happened, that's when now things started to get very, very slow for you. So this is one of the challenges that now Immutability brings here and say, describe and provide a particular alternative by saying, hey, you know what? In the context of JavaScript development or in the development, Immutability, it means that we can have now the ability to track is the state change of an object. It doesn't mean that that object won't change, not at all. It means that we're going to have the ability to keep track the state change. So we don't have any weird state change happening. We want us to know that that state change happened as expected. So that's what we started to talk about is the way of how now immutability is being addressed in the language. For example, assignment and values. So according to Kyle Simpson and also in my own experience, it's like, yeah, most of the time we haven't encountered any problems in terms of assignment, okay? We most of the time encounter problems is when we mutate the value. So that's what we have now, object.freeze, to tell the user, hey, this object is read only. So you are not going to be able to mutate that. If you want to do that, the language for us is going to protect against do that. And also, it enforces you to actually generate a new state of that, which is functional programmer says has been the best way to actually come up with some solutions. And for example, Nubank language, Nubank, they're using its Closure, okay, programming language archive. We're celebrating its anniversary with an exclusive web series, interviewing its creator. Check it out. Exactly. Reading in Closure. Closure. Like this, right? It's a general purpose. It's a list dialect. It's a way to work with collections or lists. Interesting. Closure. Mhm. Mhm. Exactly. Why did I write another programming language? Basically, because I want a Lisp as a way to work with lists for functional programming, symbiotic with an established platform, and designed for concurrency. I couldn't find one. Here's an outline of some of the motivating ideas behind closure. Lisp is a good thing, often emulate emulates, still not duplicated. Lambda calculus yields an extremely small core, almost no syntax. Core advantage is still code as data and syntactic abstractions. Well, what about standard lists, common lists, and scheme? Slow, no innovation post standardization. Core data structure mutable, not extensible. No concurrency in a spec. Common list and scheme. No concurrency in a spec. Good implementation already exists for GFM. Standard lists are their own platforms. Closure is a list not constrained by backward compatibility. Extend the code as data paradigm to maps and vectors. Default to immutability and that kind of thing. In functional programming is a good thing because immutability data first is the ability to keep track, state changing or data. First class functions could always be done in Lisp by discipline convention. Pure function language tends to strongly type static type. Not for everyone or every task. Closure is a functional language with dynamic emphasis. VMs, not OSs, are the platform of the future, providing interesting. VMs, not OS, are the platform or the future. There is something called EDX, which is a VM for that. It's a Exactly. 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 All right. Okay. 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 Yeah. I'm gonna take some notes here, right?
So read-only data structures are data structures that never need to be mutated. That's key. A read-only data structure is a data structure that never needs to be mutated ever again. You might create it and do some mutation in its creation process, but at some point you freeze it, you say it's done, it's final, it's complete, and then you move on. You use that in that final value form for the rest of the program. That actually is, there's a lot of those. There's a lot of times when we create a config object that we're going to pass in to an AJAX call or something like that. That's an object that isn't going to change, or at least it shouldn't. Otherwise, we're probably going to have bugs that we don't expect. So that's an example when we pass in an object and you pass in a configuration array or something like that. You even take a JSON response from an API. That's a value that's done. It's come back from the database. It's come back from the API. It's done. It ought to be marked as read-only because there's no reason for us to be mucking with that in some way that's going to end up creating a misexpectation and therefore a bug somewhere else in the code. Those are all data structures that don't need to be mutated. But that certainly can't be all of our data structures. We certainly can't imagine a program that would do anything useful if all of our data structures were in this read-only state.
Exactly.
Some of them, sure, but all of them in a read-only state would mean a program that was fixed and did nothing, and we could just delete it and move on. So when I take that process order function, and I pass in an order to it, you'll notice here that I'm trying to change it because I'm doing something that makes sense only for the database. I'm not even thinking about what somebody might have done with that order object after having called me. I'm just trying to make sure there's a particular flag on it before I try to save it to the database. You see the mutation there? The mutation that occurs by reference is, by definition, a side effect. We have an impure function. Of course, we have an impure function because of the database call, but we have another impurity which can create huge bugs in our program. So just because somebody may or may not remember to pass in object.freeze. I have an even more important point to make about this idea of value immutability, which is if somebody passes you a value that is in its identity mutable, something like an array or an object, then it is incumbent upon you, the author of the function, you don't know all of the call sites for this function. You don't know whether they're going to pass object.freeze or not. The best thing for you to do is to always assume that it's a read-only data structure. Always assume that you're not allowed to mutate it. Don't assume that because you mutate it and you don't see an error at that point, that nobody else is going to try to pass in an object.freeze data structure, in which case you would have a fatal failure. Always assume that you're not allowed to do line 3, you're not allowed to mutate it. So what do? We need to add a status field to it before we save it to the database. The answer is, you make a copy of the object. You make a copy of the object, which is what I'm doing on line 2, and that copy, I'm simply using the ... operator, that's object spread. You make a copy of that object, and then you can mutate it internally all that you want, because you're not having a side effect on the outside program. You should always assume that it's a read-only data structure, no matter what. So there's two sides of this issue, and don't lose track of them. One side of the issue is that when you call a function and you're going to pass in a data structure, do your reader the benefit of annotating it that you want it to not be changed. Use something like object.freeze. And secondly, and maybe even more importantly, when you write a function that receives data structures, treat it as if it's read-only no matter what. Make a copy of it, make your changes to your local copy. That's how we deal effectively with value immutability.
I prefer to follow this particular discipline, which is...
but again, that still only tells us something about data structures that never need to change. What do we do with data structures that do need to change? Well, you can't treat all data structures as immutable data structures, as read-only data structures. Some of them are going to have to be mutable. And here's the real counterintuitive thing. When you have the need for a mutable data structure, that is one that is not read-only, what you actually need is an immutable data structure. Let me say that again because it's really strange. When you need a mutable data structure, what you actually need is an immutable data structure. So what am I talking about here? What do I mean by that? An immutable data structure is one that allows not no mutation, but rather structured mutation. Structured, controlled, intentional mutation, as opposed to just willy-nilly make an assignment statement and create a side effect somewhere. It's the next level from a read-only. You should start by asking, is this ever going to need to mutate in any way, shape, or form? If so, then I don't use a read-only. I need to do something immutable. But if it never needs to change, then just stick with the plain, simple read-only data structure.
Exactly.
We only step up to this immutable data structure if it needs to mutate. So what exactly is an immutable data structure? It is a representation of the data structures that we are used to dealing with. We're used to dealing with data structures like arrays, where we can access things at index positions. We're used to dealing with things like objects, where we can access things at named property positions. It's things like that. It's data structures like that. But where you don't have access to the actual underlying data structure, what you have only is an API to access it. And the API creates a layer of control that prevents unexpected changes to the data structure. Specifically, what an immutable data structure says is unless you switch it into a special mode that allows this. So by default, it's not. If you switch it into a special mode, you can literally go in and muck with it if you have like a performance problem that you need to deal with. But in the general state, an immutable data structure says, essentially, you cannot change the data structure. You can only create a new data structure with the change having been applied. Similar to what we did a couple of slides ago when I made a copy to the thing and then I added the status field to it. It's similar to that concept. It says, listen, I need to add something to it, and the response from the API is, okay, but here's a new data structure with the change applied. I'm not going to let you modify the previous one. And the reason I'm not going to let you modify the previous one is that somebody else in the program might be relying upon the previous state of that object. They have to opt in to saying, I want your version of the object. You don't get to decide, process order, that you're going to affect something at a distance somewhere else in the app. You could return the new order, the processed order with the status field, and allow the caller of your function to decide what they want to do with that information. But you don't get to mutate it from afar. That's what I mean by saying that an immutable data structure creates a control mechanism. It creates a controlled, intentional way for the mutation to occur, and by default it simply says, let's make a whole new object. A whole new array, a whole new list, a whole new object, a whole new map, whatever the data structure is, make a whole new one of those with the change having been applied. Now the question becomes, how could that possibly be performant? How could it possibly be performant for me to make a whole new copy of this array or a whole new copy of this object every single time I need to make a change? Because the kinds of objects and arrays that we're talking about that need to be mutated probably need to be mutated a lot. Not once or twice, not 3 or 10 times, but like thousands of times a second. So the ante is high for if I'm going to change this thing over and over and over and over again so often, and I'm creating all these new ones and throwing all the old ones away, at worst, I mean at best, I just have a bunch of garbage collection, but at worst you consider all the CPU churn of making all those copies over and over again. And this is where the real power of an immutable data structure comes in. Because the way immutable data structures are designed is designed specifically with this optimization in mind. In theory, in functional programming, we just say, no, you don't make a new thing, you don't make a change to a thing, you make a new thing with the change applied. But in practice, that means real cost, like garbage collection and CPU.
Exactly.
And so it is the job of an immutable data structure to mitigate that real practical cost so that we get closer back to the theoretical benefit of what an immutable data structure is. So if you use an immutable data structure, what it's actually going to do is not create a whole new copy of the object when you try to change a property, but rather make a new object with the new information in it and internally have a pointer back to the previous one. It's actually a little bit like a Git repo, where every time you've committed something, you're just storing a diff compared to what it was before. An immutable data structure is essentially conceptually like a Git data structure, where each new object in the chain that you've created is just a diff on the previous object. It stores internally that there's now a new property or that a property's been changed or something like that. And so you're not paying nearly as much of the performance penalty CPU, and you're not paying the garbage collection penalty. In the general sense, there's certainly corner cases here, and it's why immutable data structures can allow you to opt in, for a time period. You can sort of crack it open, make some changes, and then lock it back together. Those things have to exist because sometimes we have performance bottlenecks that we need to deal with. But in the general sense, we want to just use the data structure in that conceptual way and allow it to abstract away those performance optimizations for us. So, how do we get immutable data structures? We do not, at the present time, have immutable data structures natively in JavaScript. There have been a couple of rumblings from some people on TC39 that maybe someday that will happen. But you need to understand that when somebody says, oh yeah, somebody on TC39 has talked about maybe it happening, that means that we might get it a decade from now. That's not like, oh, it's going to happen in 3 weeks or 4 months.
Doesn't mean, if you hear some, oh my God, and I love it. We don't have exactly natively support of this immutable data structure or this mechanism in which now, instead of us having to create this particularly new state that, of course, anytime you create that new state is use a CPU as well as memory, all right, for each one of those, right? And you don't want to do that. That's one of the trade-off here. You are limited by the resource, GPU, CPU, and memory. So because of that, we need to find a way, is a mechanism to mitigate those kind of challenges. So that's what we have, is this immutable data structure, or this particularly data structure that now allows to detect those changes when that happens, and now have a reference or create a new reference or a new version of this object. So as Kyle Simpson mentioned, is like you're going to have now is anytime you want to mutate the state of this read only, you're going to have now a new state that points to the previous one, but with the updated or with the change that you already made that. And I think that Immer is something that is doing behind the scenes for that.
So, how do we get immutable data structures? We do not, at the present time, have immutable data structures.
And not only that, but when he mentioned is that when you hear someone that's give you perspective. So when you hear someone that is on the TC39 committee, the talk and discuss about that, that's something that can take decades to be implemented
natively in JavaScript. There have been a couple of rumblings from some people on TC39 that maybe someday that will happen. But you need to understand that when somebody says, oh yeah, somebody on TC39 has talked about maybe it happening, that means that we might get it a decade from now. That's not like, oh, it's going to happen in a few weeks or a few months. The timelines that we're talking about here are, oh, it's been talked about for the last 5 years, and now there's like a first proposal, and then 4 years later they've vetted, and now it's finally landing. So we're not talking about this sort of stuff landing natively in JavaScript anytime soon. But it's at least encouraging that some conversation has started about it. Some people in that realm have started to say, maybe this would be useful for JavaScript to have built in natively.
And and there is a reason why I choose the web over other platforms, because here on the web is where we can now provide much value, is when we can interact, we can share with other people's thousands of miles away, over the globe. So I can see you, you can actually see me. I don't know where you are located, but you can actually see me through a browser, most likely, right? Or through an application that communicate to other applications, right? Which means here I'm not broadcasting this, I'm just recording this video, and then I go to upload to the YouTube channel, and then once you navigate to YouTube or you access through their apps, okay, then is when you can actually see this particular content, this particular video. And that is something that I find valuable, because as humans, we not only have the ability to self-destruct ourselves or kill each other, but we also have the need to share in terms of resource. Whether it is natural resource, you have water, shelter, light, fire, clothes, woman, slave. I'm not a big fan of that, but exists, all right? Gold, silver, technology, we need to share, okay, to solve those particular problems. Oh my God.
And there would be a huge benefit to the language being able to highly optimize these sorts of things that we're talking about.
Yeah.
In the interim, in any place where you have a data structure and it is important for you to manage the mutations to that data structure, you're going to need a library that provides you an immutable data structure. And there are a couple of major ones out there that you will hear about. Probably the most common of those is called Immutable.js. It comes from the folks at Facebook. So if you want to check out Immutable.js, they've got a bunch of great documentation. It has a huge...
That makes a lot of sense. So Immutable.js. Interesting. Immutable. Getting started. The case of immutability, JavaScript first API, nested structure, equality treats, collection as value, batching mutations, lazy sequencing, that kind of thing. Oh, there is a video about that. Interesting. Holy F. What a way to introduce to this, man. Look at this. Oh, all right. Okay, look at this. I was looking at this, right? Immutable.js, and it looked like, ooh, interesting, yeah. And then when I click here, okay, and they say, okay, holy F, Alan K, zero pack creator of small tag. The last thing you want any programmer to do is mess with internal state. Even if present figuratively, it is unfortunate that much of what is called object-oriented programming today is simply old-style programming with fancier construct.
Welcome back. So, the great thing with React is that it's not just a view layer, but it makes everyone rethink.
It's this one.
Immutable change tracking actually solves this problem, and it does it extremely performantly. Here's how that works. So this is an example from Immutable again. I'm going to make a map, an immutable map, with key value pair. And I'm going to set that key to foo and get a new map. I'm going to compare them, different objects. Returns false.
Exactly, but this is assignment, right? No, they're not the same, because what it's doing behind the scenes, JavaScript is to say, hey, I'm going to now is in this memory address, okay, I'm gonna put this object here map, good, and then the second, which is now the label, then I got to create now this another reference. So now that I have another reference to create is this object where I have this reference, which means I'm gonna put this, I'm gonna mutate that, okay? But what it's doing is to having different places of where I'm going to put now my data, even though that data refers to the same thing, okay? Even though that data refers to the same thing, for example, like this, okay? Oh my God. I have these two space or two slot in memory, okay? So even that these two things refers the same object here in memory, let's say a coin, okay? I'm using these slots here in memory to store a coin, and even if I want to have another copy of the same coin, I can do that, right? But what it's doing here is that, of course, that's false because it has different positions on the on memory, right? They have different address in memory.
Awesome, cool, something changed. Okay, back to that first map, which didn't change, right? I'm going to set key to value. It's going to figure out, like, oh, that already was value. So it's going to no-op. It's going to return itself. I compare them. It's true. Cool. Nothing changed. That's the whole demo.
Exactly. That's the whole demo. That's the whole demo. Interesting. Exactly. And now it's saying, now, hey, no, they are the same. I'm having as the same ref. I am using the same space, the same address for that. Because I'm using the same address that has that value for that.
Demo. All right, well, let's do it for deep structures, because, okay, deep structures were hard, right? So here's a map of maps, right? Foo and bar each have a value to key. So I want to do the set in. So one tricky bit with immutable structures is when you want to mutate them, previously we just like work our way down and like futz around and then get out of there, but now we actually have to be really explicit about the change we want to make. So we want to crawl into foo, val, and then set that to 500. So of course, that's going to result in a whole new map of maps, so we expect that to be false. And if we get foo from both the new one.
So you get this first, which I have reference to this set in foo val, which is foo val of 500. Okay. So it means that the second and the first is different. That's right. But if you say second dot get foo and the first dot get foo,
in the old one, we expect that to return false because we've edited that. But if we reach in and get bar, it's true because we just recycled it. So the whole thing did, change from the top. But as soon as we get to a leaf that hasn't changed, we can detect it with reference equality, which is free.
Which reference equality?
Okay, I want to talk about memoization. You guys have heard of this super powerful optimization technique. Let's say I have some expensive function. I'm going for a memoize function for JavaScript, and this was the one that, and a slow one. So I ran this, And it turns out that for my 1 million elements sum, that it's more expensive to memorize it than it's not. Here's a new version. Okay, I dumbed it down a little bit, and I'm only memoizing the previous call, not all calls. But you can imagine I could use a map or something. But all I want to do is like check the previous arg. If it was the same, then I could just return the previous result. Otherwise, I'm going to store the previous arg, run the function, and return the previous result. So I do this. It's like, okay, it's expensive. Do it the second time. Sweet, it's free. Then I push onto my array. Uh-oh. Right, it was the same array. I can't push into it and expect this equality check to work because, of course, it's the same array. That doesn't work. So let's replace it with a mutable list. So I have a list of 1 million elements instead. I'm going to sum them. And the second one is free. Cool. By the way, same implementation of memwise. Haven't changed anything. Now I'm going to push into my list. I'm going to get a new list. I'm going to call sum. Sweet, it works. That was easy. This is relevant because in React we have this thing called should component update. I picked out change tracking and memoization specifically because and Jason showed you guys how this works.
But this is immutability. Flow and TypeScript. The case of immutability, and the using is now for that. But now they're using something called Immer. Immer, which is the whole reason of why we actually are looking is at Immer, right? Basics here. No, take me to the GitHub documentation right now. Here, I want to take a look at the Immer. Create the next immutable state by mutating the current one. Exactly. Create the next immutable state by creating, by mutating the current one. Okay. This was something that is in 2019. Holy moly! Create the next immutable state tree by simply modifying the current tree. So I'm going to create a new tree state or state tree by mutating or by modifying the current tree. Which is unlike so unlike is immutable GS, right? Now immutable GS like this, immutable GS, immutable persistent data collection for JavaScript, which increase efficiency and simplicity. There are 32K star. There are more than 215 contributors. Okay, 3 months ago, and the other was Immer, which is 26.6 thousand K star. That's quite interesting. Let me actually keep up the pace here with this. Another star here. Okay. And it is used by 10 million people. Yeah. They don't show how many people they use this, but I think there must be a lot. There must be a lot. So, interesting. Immutability here. Immediate. 2018. Introducing Immer. Immutability the easy way. Structural sharing. Or entire new library for your data structure. Immer operates on normal JavaScript objects and array. Exactly, unlike immutable, GS, all right? When you have now this, Immer say, hey, I'm gonna work on this draft, and then you can now operate into that. Immer remains type doing deep updates. Immer doesn't suffer from any of that. It operates on built-in JavaScript structure, perfectly understand any type check or modify data like that, as well as querying and all of that kind of thing. Exactly. How does Immer work? Well, two words: copy on write and proxies. Exactly. Hey, do you want to read? No. Return the base. Yes. Let's go to clone this. Right? This is if you want to read this. It was modified. Yes. Clone it. It was not. Return the base. If you want to read that, it's going to pass through the proxy, which is an object that wrap this target object. And intersect is the built-in internal object methods. For example, the setters, the getters, the has-on property, and that kind of things, and then act upon that, and then allow you to define some instructions on that. So then you have modify. This is, hey, if you modify, yes, please return a new clone. If you don't modify, clone base, mark modify, and mark patterns, and then clone. Proxies are available in all recent browsers, but still not everywhere. The most notable exceptions are Microsoft Internet Explorer and React Native for Android. For this target, Immer shipped with a pure ES6 implementations. Schematically the same, just a bit slower. You can use it by using import products from Immer. Performance is this. So when you no freeze, you got this. And when you freeze, you got this. Immer performance. Time, milliseconds to update 10,000 elements. 10K in an object. 10K object in a set of 100K. Lower is better. Oh, this is when you use object of freeze. Or with no freeze, reducer. Immutable GS. Immer proxy. And Immer EX6. Okay, this is when you mutate that. Oh, okay, the CPU and the memory is being used, but in terms of what? This is time. Time in milliseconds to do that. Deception mutate. Reducers. Damn, son. Native reducers. Immutable GS. With freeze and no freeze. Immutable GS to GS. Immer with proxy. With no freeze. And freeze. Alright, and then Immer for that. The usual mantra holds here. It is always better to optimize for developer experience than for runtime performance, unless proven by measuring here. This is something interesting. This is something interesting here. That'll be all for this video. Take care. Bye-bye.